Hi friends, a warm welcome to Pharma Baba Net YouTube channel. In this video, we will learn how to scale up blending and lubrication unit operation. So let's start the video. So dear friends, as we know, scale up in the pharmaceutical manufacturing process is very important for controlling the quality of pharmaceutical products. Blending and lubrication are important unit operation which ensure mixing of pharmaceutical additives and lubricants. So whether a process is a direct compression or it is a wet granulation, well, blending and lubrication are important unit operations. And to ensure the quality in the products, a proper scale up for these two unit operation is required. Of hydrophobic lubricant such as magnesium citrate is the most frequent used lubricant to improve the flowability of the granules. But magnesium citrate has a negative effect on the tensile strength and dissolution of property of the tablet. So what I mean that a proper scale up strategy is required to scale up our blending and lubrication unit operation. In the lubrication process, most of time we use magnesium citrate, which is a hydrophobic lubricant, and if we over lubricate, then we can face issue of dissolution or negative tensile strength, the hardness of the tablet. Or if we less lubricate, if we will not do the optimum lubrication, then we can observe the sticking or other related issues. So in this video, we will discuss how to scale up the unit operation, blending and lubrication properly. So let's go to the next slide. So, dear friends, we will discuss that the unit operation, blending and lubrication, what are the variables which may affect the scale up of the blending and lubrication. So, the all variable we can summarize as mixing condition. So, it involves blender type, like type of blender, what blender we are using in this lab scale, and what blender we are going to be used in the pilot or pivotal stage. That blender type will affect our scale up of the unit operation, blending and lubrication. Then fill level means occupancy studied in the lab scale and occupancy proposed for the pilot or pivotal scale. The rpm, rotational speed of the blender in the lab scale, and what rpm is proposed in the pilot and pivotal scale. Then mixing time, blending time or lubrication time, what time is in the lab scale and what time proposed for the pilot and pivotal scale. So we'll go to the next slide and we will see how these mixing condition variables can be optimized and can be proposed so as we can achieve the proper scale up for the unit operation, blending and lubrication. So friends, first variable factor is blender type. So thumb strategy is to keep the same blender type in the lab scale as well as in the pilot and pivotal scale. But sometimes this liberty is not in our hand. So broadly, we can discuss how to optimize this part of the this variable. So blender can be broadly divided into the three category we can divide. First is the diffusion blender, means tumbling. Second is convection mixing. Third is pneumatic mixing. Diffusion blending means particles are in the diffusion in the diffusion blender. Particles are reoriented in relation to one another when they are placed in random motion, and inter particulate friction is reduced as the result of bed expansion, usually within a rotating container, also known as tumbling blender. So it is a blender. It is either the principle is either it is a cone or it is a bin, and by the mixing, by the rotation, we achieve the uniformity and mixing. What is our requirement depend on that case. So this is a diffusion blender. So diffusion blender examples are like V blender, double cone blender, slant cone blender, cube blender, bin blender, horizontal vertical drum blender, static continuous blender, dynamic continuous blender. These all blender are diffusion blender. So whenever we are scaling from one or in the diffusion category, our scale up chances of a good scale up are will be more accurate. First strategy will be like that. If you are using the V blender in the lab scale, use V blender in the pilot and pivotal scale also. But if this is not possible because of some reason, So blender type, at least use the blender of the same category, like diffusion blending. Don't go from the diffusion to the convection mixing blender. Use diffusion blender only. Means if you are using a bin blender, then use bin blender only. Not use a bin blender with the intensifier, because it will differentiate your scale up strategy. So first thing, blender type, keep same blender type, or at least keep the principle of the blender type same. So diffusion blender, these are the example of the diffusion blender. Then convection mixing. The convection mixing is particles are reoriented in relation to one another as a result of mechanical movement, also known as pedal or flow mixing. So some force is applied, so mechanical force is applied to get a uniform blend. Example are ribbon blender, orbiting screw blender, planetary blender, four-brake blender, horizontal double arm blenders, horizontal high intensity mixer, vertical high intensity mixer, diffusion mixer, tumble with intensifier or agitator. If agitator is there, then it will come in the convection mixing. So keep the same blended type. Third type of the blender are pneumatic mixing. Particles are reoriented in relation to one another as a result of the expansion of the powder bed by gas. So it is less commonly used in the solid oral industry, though this is also a pneumatic mixing, also a type of mixing. So what I mean in conclusion, that use the same blender type, at least use the same blending principle at the lab scale and the pilot and pivotal scale. So, dear friends, blender type we understood. Then second is how to decide the blending RPM, how to scale up our blending RPM from the lab scale to the pilot or pivotal scale. So, very simple. We all know the dimensionless number, fraud number. Same fraud number will be used in the most of cases to calculate the RPM at the to propose the RPM at the pilot and pivotal scale. So you have to maintain a constant fraud number. So either you are doing a scale up or you are doing a scale down, you have to maintain a constant fraud number. So simply way, if you are maintaining the constant fraud number from scale 1 and scale to scale 2, then you will get a equation radius 1 into rpm 1 square equal to radius 2 into rpm 2 square. What it means, that radius 1 at your first scale, for example you are scaling from the lab scale to the pilot scale or pivotal scale, then your radius of your first blender, what is the radius? See, if you see, the all blenders are rotated around the axis. Okay, there is one axis around which blender will be rotated. So when it will be rotate, it will making a circle. So radius of that circle you can easily calculate from the axis, means center point of the blender, to the circumference of the circle in which it is rotating. So by that you can calculate the radius for scale 1, means level scale, also you can calculate the radius, and for scale 2 also you can calculate the radius. You can take your help of your engineering department to get the this radius. This value should be you can calculate in the meter. Then rpm 1 square. See, in the lab scale you will optimize your process, so whatever rpm you are keeping here now, that is the rpm 1. Okay, and then radius 2, that you can calculate at the second scale, means pilot or pivotal scale, and rpm 2 is your what rpm you will propose for the scale up scale, means pilot or pivotal scale. So by this equation you can determine the rpm 2, because rpm radius 1 you know, rpm 1 you know, radius 2 you can know the you can calculate. So you can easily determine the rpm 2 value. So this is an example. We will see how we have calculated in the lab scale. This is the radius value is arbitrary value. So just for a correlation example, I put it these values. So for example, in the lab scale, the radius is 0.1 meter. So RPM is the 20 RPM. It is optimized. So we calculated the fraud number. I will show you in Excel sheet how to calculate. So we calculate the fraud number. Then when we went for the pilot, we kept same fraud number. By that we calculated the radius by measuring simple physical measurement. We calculate the rpm, it was 12 rpm around for the pilot. Similar way we calculate the rpm, and it was 8 rpm for the commercial scale. So friends, we will now we'll calculate how we calculate this pilot scale RPM or commercial scale RPM, how we calculate. Just we will see a practical example. So just I am taking my Kelsey. So just we'll see the same equation we are going to use. Radius 1, which is 0.10 at lab scale, we optimize our process. So we will take the lab scale radius 0.10. Okay, then multiply by rpm 1 square means lab scale rpm square means 20 into 20. So multiply by 20 into 20. Okay, so this will come around 40. So divide by radius 2. Second scale, suppose we are going to scale up the pilot scale. So second scale radius is 0.27. So we will divide by 0.27. Okay, so it will come around 148.148. So we will take a square root to get the pilot scale rpm. So here we will take a square root, so it will come around 12.17, which we mentioned here, 12.17. So a process in a blender of having a radius 0.10 optimizes 20 rpm. So for that process, if we want to scale in a pilot scale of having radius in the blender 0.27, we have to keep 12.17 rpm so as to keep the same Froude number. So by keeping the same Froude number, we obtain the rpm of the pilot scale, second scale. Okay, same strategy we will use to get the rpm of the commercial scale. So based on that, based on this principle, by keeping the constant Froude number, we can calculate the rpm of the any scale. So now we will see, friends, how to calculate the blending time. So we understood that how to calculate the blending RPM. So across the scale, we can calculate the RPM. For example, a process optimized at the lab scale at 20 RPM, we will keep 12.17 or 12 RPM at the pilot scale. And similarly, we can keep 8.3 RPM at the commercial scale. And these RPM were calculated by keeping the constant Froude number. So friends, if we are mixing some excipient, for example, talc, which is not known to impart any change in the physicochemical properties of the blend, then we will go with the constant number of revolution approach. Means if our sole target is to mix the blend uniformly, and we know from the development experience and based on the literature that if we mix for some increased number of for some longer time, then the physicochemical property of the blend will not change, then we will go with the constant number of revolution approach. What it means, for example, in the lab scale we are mixing for 5 minutes at 20 rpm, so our revolution will be 20 into 5 means 100 revolution we are doing. So same 100 revolution, near about 100 revolution we will follow for the scale up. For example, in the pilot scale we already calculated rpm 12, so 12 at 12 rpm we will mix for 8, at least 8 minutes, so that our revolution will be constant. So based on that we will decide our blending time. For example, similar in the commercial scale, we will mix for the 12 minute at the reduced rpm, that is 8.3 rpm, so that our revolution will be the constant. So this approach means constant number of revolution approach generally follows in the blending. In the blending approach means to calculate the blending time. What blending means the in this excipient will not impact the physical chemical property of the blend. For example, if I cannot calculate the same way for the magnesium stearate, because if I will overmix magnesium stearate, then it may change the physicochemical property of the blend and the product. So this type of approach is used for mixing at the blending stage blending stage only. So depending upon your process, you may use this approach to calculate the blending time. Dear friends, so far we discussed about the blender type, we discussed about the blending RPM, we discussed about the blending time, how we can calculate and correlate lab versus pilot or commercial stage. This is our scale up strategy for these variables. For lubrication time, we already discussed that some excipient like magnesium stearate, they are hydrophobic in nature, and their mixing time, their time of mixing is very crucial because they can change the blend property, they can change the physicochemical property of the blend and the drug product. So their time of mixing is crucial. So for these type of excipient, for lubrication time, we can use this equation to calculate the number of revolution, or to calculate the blending, to calculate the time, blending time. Okay, this equation you can find in the QBDIR example also. Most of places this equation is followed, and it gives a good scale up correlation. So if the best size, generally we are aware of the our pilot scale or pivotal scale best size. We are aware of the what blender we are going to be used. So if we know the best size of our scale up stage, we know the blender size of our scale up stage, the number of the number of revolution or the time of mixing can be calculated by using this equation. So this is at the upside, the first blender volume is there 1 by 3, blender volume raised to the power 1 by 3 multiplied by the head space. Head space is nothing, the free space remaining. So you can calculate it by 100% minus the occupancy of the your occupancy of the your base size, means 100% minus blender fill level. It will give the head space, multiply by the radius of the blender first scale, then the second scale for which we are calculating the number of revolution. So for that stage blender volume raised to the power 1 by 3 multiplied by head space of that stage. So this simple equation we can use to calculate the lubrication time at the pilot and pivotal scale. So friends, now we will see practical application of this equation. So in the same example, we'll see, let's go to the Excel sheet. For lubrication time, what we are doing, we are using a different equation which also incorporate the headspace function also. So we already have seen the equation. This is the equation. This equation will give you the number of revolution of the second stage. So if we divide the number of revolution with the RPM of the second stage, we will get the lubrication time. This equation, just see once again equation. It is the lab scale, scale 1 I will say lab scale, and scale 2 I will say pilot scale. So lab scale blender volume divided raised to the power 1 by 3 means we have to take cubic root of the blender volume multiply by the head space of lab scale. Head space means 100% minus the occupancy of the blender at the lab scale, multiply by the radius of the lab scale, divided by the volume of the blender at the pilot scale, multiply by the head space of the blender at the pilot scale. So let see a practical example. This is a lab scale. So, suppose lab scale blender is 17.6 liter capacity, just arbitrary capacity which I taken from the QBD IR example. So just I am giving an example. You can place your actual values in this sheet to calculate. Suppose our lab scale center point batch is at the 49% blender occupancy, and we are lubricating 5 minutes. Right now we are scaling up in the pilot with the 150 liter blender capacity. The radius we know 0.27. Okay, so the occupancy at the that stage is 56%. So what we'll calculate the number of revolution with that equation. So v1 by 3, so v1 by 3 means 17.6 1 by 3. So in Excel you can calculate it by using power function divided by d7 means this 17.6 blender volume at the lab scale, comma 1 by 3. So it will give 1 by 3 v raised to power 1 by 3, multiply by we required headspace. So at the lab scale 49% is the occupancy, so 100 minus 49, 51, multiply by the number of revolution at the lab scale. So we know the 20 rpm was the lab scale rpm and 5 minutes is the lubrication time. 20 into 5, 100 will be the number of revolution at the lab scale, divided by the v1 by 3 of the pilot scale, means 150 1 by 3 power f7 150 comma 1 by 3 it will give v raised to the power 1 by 3 at the pilot scale, multiply by the head space at the pilot scale. So occupancy at the pilot scale is 56%. 100 minus 56, 44% will be the occupancy. We'll calculate it. It will give us the number of revolution proposed for the pilot scale. It will come around 56.7. Suppose we are rotating our blend at the 12 rpm, so 56.7 divided by 12, it will give a 4.7 minutes lubrication time. Similar way, as the blender capacity will change, as the batch size will change, as the occupancy will change, we can calculate the lubrication time. Okay, so in this, number of revolution will be not equal. In this, we will calculate the head space also, to determine the lubrication time for the pilot and commercial scale. So this is the approach which we will use to calculate the lubrication time, so that we will not we should not over mix the hydrophobic excipient. Okay, so that our so that to get a constant blend characteristics, so we use this equation to calculate the lubrication time. So for blending, we will go with the number of revolution approach. For the lubrication, we will go with the this approach. So all variables now we discussed, we can calculate our blending our this blender rpm also by using the fraud number, blending time also by using the number of constant rotation, and lubrication time also by using this equation. Dear friend, thank you very much for your time. Hope you now you understood, or you now clear about how to scale up the blending and lubrication unit operation. Thank you very much for your time. If you like this video, you can share in your social media platform, so that more people can attach with us. And you can subscribe my channel also. You can write me on my mail ID, which I written in this last slide, so that if you're any I can add, if you can share your number to me, so that I can add you in group, and any personal discussion is required, any more clarity is required, so we can discuss together, and I also should benefit it by your knowledge also. So friend, I'm really very sorry that this video is posted very late. I got some email also, so all topics I will cover as soon as possible. Due to some reason, I'm not able to post the video for this gap. So now I will try to post new topic every week. So thank you very much. See you in the next video. Thank you.